Welcome back to this video tutorial. We can discuss about the internal architecture of 8051 microcontroller. This is the overview of our internal architecture. Here we have the processing unit and it can process 8 bit of information. And the internal bus structure can transfer a maximum of 16 bit of information. Okay, and here we have this oscillator circuit. This oscillator circuit can generate clock pulses to this system. And here we have the interrupt control unit, can control various interrupts request coming from external peripheral units. And here we have memory system. Here we have both ROM space and RAM space. Okay, this 4 kilobytes of ROM and 128 bytes of RAM is internally present with this 8051 architecture. That means this 4K byte of RAM space and 128 byte of RAM space is embedded inside the 8051 chip itself. Here we have a timer unit. With this timer or counter unit, here we have two registers, timer 0 and timer 1. Okay, this T0 and T1 registers are present along with this counter or timer unit. This is used for performing countdown operations in association with this oscillatory circuit or in association with the clock pulses generated by this oscillatory circuit. Okay, so this counter or timer unit is actually used here for performing countdown activity. Okay, in order to store the timing information, here we have two registers T0 and T1. Okay, and this countdown activity is based on the clock pulses available here in the system, and the clock pulses are generated by an external oscillatory circuit. Right, now here we have a bus controller circuit. It can control the entire data transfer activity to this system. And here we have 4 different IO ports, P0, P1, P2 and P3. These are used for transferring input output data, and using a single port we can transfer 8 bit of information at a time. Okay, and this particular port P3 is also used for transferring data in a serial mode of data transmission. That means the system can interface with various peripheral devices that can support serial data transfer also. Okay, so this P3 port also supports serial data transmission. Okay, and this different port like P0 and P2, these two ports used for transferring IO information as well as address information. And this P1 port, which is a dedicated IO port. Okay, and all these are the units associated with this 8051 internal architecture. One more, this particular interfacing serial port interfacing unit, which is used in order to support or interface a device that supports serial mode of data transmission. So with the help of this serial port interface unit, using this P3 port, this 8051 it can also support serial mode of transmission. Okay, using this P3 port and using the serial port interface, we can perform serial mode of data transmission with external peripheral units. Okay, and along associated with the serial port unit, here we have two pins which indicate serial mode of transmission and serial mode of reception. Okay, so all these are the components of 8051 block. Next is the pin description of our 8051 microcontroller. So first 8 pin 1, 2 up to this 8 indicate port 1 P1. Okay, so this 8 pin of P1 is used for transferring input output data. That means P1 is a dedicated IO port. And 9th pin is a reset pin, indicate or is used for resetting the system. Okay, and next is about 10th and 11th pin. These two are the pin associated with serial interface unit, which indicates serial mode of transmission and reception. And 12th and 13th actually indicate an interrupt signal. These two indicate in external interrupt 0 and external interrupt 1. Okay, these two pins are used for handling external interrupt request. And T0, T1, 14th and 15th pin, like this 12th and 13th, these two indicate timer interrupt. Okay, and 16 and 17 actually indicate read operation and write, memory read and write operation. And for this 14 and 15 actually indicate timer interrupt. This timer interrupt actually occurs while happening a situation like timer register overflow, like T0 register and T1 register overflow. In that situation, this timer interrupt will occur. So whenever such a timer interrupt occurs, corresponding signal variation will happen here in this two pins, in pin 14 and pin 15. This write and read signals are actually used for memory read and write operation. And these two 18th and 19th pin indicate XTAL2 and XTAL1. These two are the input to our oscillator circuit. Oscillator circuit actually generate necessary clock signals in order to synchronize the system activity. And 20th pin is the ground pin. Okay, and 21st, from this 21st to 28th, this 8 pin for port 2, P2. These 8 pins are actually worked in a multiplexed mode of operation. These 8 pins of P2 can be used for transferring IO information as well as address information. Okay, so this pin can use for input output data transfer as well as for transferring a higher byte of address information. That means from A8 to A15, higher byte of address information. Right, next is about this 31, 30 and 29th pin. 29th pin is a PSEN, which stands for Program Store Enable pin. It is used to read a signal from the external program memory. PSEN, Program Store Enable pin, which is used for reading a signal from external program memory. Okay, and 30th pin. 30th pin is an address latch enable pin. This address latch enable pin is activated, and when it is activated, this indicates that the port P2 and port P0 actually hold address information or transferring address information. So whenever address information transfer takes place using this P2 and P0, then ALE pin become high. Next is this EA pin. EA means external access input. It is used to enable or disable the external memory interfacing. So whenever this EA pin, external access input pin, become high, then only we can access external memory. Okay, so for activating, enabling or disabling external memory interface, we can make this EA pin. Okay, next 32 to 39, the 8 next pin indicate port 0 pin. These are also multiplexed pin used for transferring IO information and address information. Whenever this ALE pin become high, then only address information transferred using this P0 along with P2. Otherwise, this indicate IO data transfer. And the 14th pin indicate voltage applied to this system. Okay, or power supplied to the system. Next is the internal architecture, detailed architecture of our 8051. Here we have the ALU, right? Associated with this processing unit, we have various registers, and like accumulator registers and some other temporary registers, and associated with this we have the processor status word. Okay, processor status word actually indicate the status of our processor. So PSW is actually an 8-bit information, and each bit indicate various status information. This CY indicate a carry flag, AC indicate auxiliary carry information. Carry flag become 1 when after an arithmetic operation whenever a carry value occurs after the MSB bit, or from the MSB bit if a carry occurs, then this carry flag value become 1. And for the nibble operation, for the third position if a carry occurs, then auxiliary carry flag become 1 in case of a nibble operation. And for the third position if a carry occurs, then this auxiliary carry become 1. And this next bit indicate F0, that indicate a user defined function, that means the user can define its value based on its purpose, based on the application. User can define or user can use according to the application or the requirement inside a program. Next 2-bit RS1 and RS0 is used for register bank selection. So in 8051 and for programming, here we have different bank of registers. Each bank is associated with 8 different registers. For a program, we can make use 8 different registers comes under a single bank. And here we have 4 different banks. Okay, so using these two bit of information, RS1 and RS0, we can decide which bank of register is going to use in our program. Okay, so that information is given here. If it is in the form 00, that means register bank 0 is going to use in our program. Okay, the register bank available in an address value from 00 to 07. And if it is in the form 01, that indicate register bank 1 is going to use in our program. Right, so the register bank 1 is available in an address location from 08 to 0F of our internal RAM memory space. And if here it is of the form 10, then it indicate inside the program we are going to use register bank 2, and the register bank 2 is available from an address location 10H to 17H of our internal RAM memory space. Similarly, for the third register bank, it is the status of our RS1 and RS0 as 11, and the third register bank, bank 3, is available from address location 18H to 1FH. Right, we can consider this one in more detail once more in internal memory organization part. Okay, next is about the overflow flag. This one become active when an overflow condition occurs. Next one is also a user defined bit. And last and finally, the last or least bit indicate the parity flag. This is used for indicating even parity of our data. Okay, so this is about the processor status word register of our system, which indicate the status of our processor. Okay, now here we have 4 different ports: port 0, port 2, port 1 and port 3. And these 4 ports are associated with drivers and different latches. And these latches are usually used for temporary storing the data to be transferred or data to be received through this port for a temporary storage. So these latches are used for temporarily storing the data associated with this 4 different ports. Among these 4 different ports, port 0 and port 2 used as a multiplex data and address port. That means it can be used for transferring IO and address information. But port 1 is a dedicated IO port, simply used for transferring IO information. But port 3 has also some different functionality. It can used for data transfer, and it can also use for transferring serial data transfer. and used for transferring timer information, and also for transferring interrupt request and interrupt regarding information. So port 3 has different functionality. It can transfer IO data, it can transfer serial mode of data transfer, it can transfer timer information, and also can transfer interrupt related information, right? And here we have the stack pointer, and this stack pointer is actually used for pointing to the top of the stack memory area of our internal memory. Okay, similarly from our 8086, the stack pointer is actually used for pointing to the stack top of our stack memory area of our system. Okay, and here we have this registers like program counter increment and program address registers. All these are actually used for indicating the program memory space of our system. Okay, this program memory is actually the raw memory space. Okay, so this program counter actually hold the address of the next instruction to be accessed from this raw memory. This PC increment unit is actually used for automatically increment the value of program counter after each instruction fetch operation. Okay, and buffer and program address register. Program address register is used for storing the current address of the instruction to be accessed from the raw. And buffer is actually used for temporary storing the accessed data. Okay, and this DPTR is a special register, data pointer register. This is a special function register and is basically used for accessing data from external memory. Whenever some external memory is interfaced with the system, then this DPTR register must use in order to access data from external memory. So keep in mind, this DPTR, data pointer register, is always used in order to access data from external memory. If we want to access data from internal memory, we can simply use our accumulator register. But in order to access data from external memory, we need to point that location using this DPTR and access the data using the location pointed by DPTR to accumulator register. Right, so here we have the ROM space in which we can store the program, and for accessing the program from the ROM memory and for writing something to the ROM memory, we have this program counter register, program counter increment unit, this in temporary buffer space, and program address register. Similarly, here we have this RAM space in which we can store data, program related data. And here we have the RAM address register in which we can store the address of the data currently accessed from the RAM, or address of the memory location which is currently accessed by the processor. Okay, now here we have this timer unit and instruction registers. Instruction registers are actually used for storing the current instruction which is fetched from the memory. That means after fetching the data from, not the data, after fetching instruction from the memory, it is placed inside the instruction register. Then we can decode the instruction using the information available in the instruction register and identify what operation or what opcode we want to perform and on which operand we need to perform that operation. So after fetching, the instruction is placed here in the instruction register. After completing a fetch operation, this program counter value is automatically incremented to point to the next instruction inside this ROM memory. Okay, so this is the difference of program counter and instruction register. Instruction register actually hold the instruction which is going to execute by this ALD, and program counter pointing to the address of the next instruction to be executed by the ALD. Currently executing instruction is available in instruction register, address of the next instruction to be executed which is available in program counter. And this timer and control unit actually used for controlling this timing and counting activity of our microcontroller based system. An oscillator circuit is available here which provide the clock pulses required for synchronizing the activity of the system. Okay, and this timer and control unit based on the timer register available in the timer and control unit, we can store the timer information, and this unit can start countdown operation based on the clock pulses available from this oscillator. And it can generate various control signals like PSEN, program store enable, address latch enable, external access point enable, and reset. So all these are the control signals generated and received by this timing and control unit. This timing and control unit can control and manage the timing and control activity of the entire system. And this timing management synchronization activities based on the clock pulses provided through this oscillator. Okay, PSCN actually means enabling the external program memory, and external access point signal is actually used for enabling external memory interfacing unit. ALE is indicating whenever the address information is available in our bus through this port 2 and port 0. Okay, RST actually used for resetting the system. So all these are about the internal architecture of our 8051 in detail. Okay, so in our next video we can consider the internal memory organization of this 8051 system. Okay, thank you.